Okay, so we're going to work through review set number 9, and also the work the week 9 problems. Let's start with our review. So we start with a couple of differentiations. So we want to take the derivative of cosine of x squared minus sine of x cubed over cotangent of x to the 4th plus tangent x to the 5th. Okay, I mean, you're not going to find such a function in any immediate application, but it's a good practice problem. I'm not going to try to simplify anything. I'm going to just apply the quotient rule. So in the quotient rule, what you need to do is take the derivative of the numerator. So let me prepare the space for it. Multiply it with the denominator. Then subtract from it the numerator times the derivative of the denominator. And then we need to divide by the denominator square. So actually, let me put in the things that do not change. So I can put in the denominator right here. That won't change. I can put the numerator right here. That doesn't change either. And then I will put the denominator right here. Now, let's find the derivative of the numerator, which is what? The derivative of cosine is negative sine, and we also apply the chain rule. So this is negative sine of x squared times 2x minus the derivative of sine is cosine. So we have cosine of x cubed, and by the chain rule, we should multiply by the derivative of the inner function. So that's times 3x squared. Let's do this for the denominator. So the derivative of cotangent is negative cosecant square. So negative cosecant square of x to the 4th times 4x cubed plus, and the derivative of tangent is secant. So secant square, secant square, not secant, of x to the 5th times 5x to the 4th. So just to make sure that this can be better understood, what I just wrote here is secant square of x to the 5th times 5x to the 4th. Okay, so that's the derivative of this function. And then we want to take the derivative of cosecant of 3 to the x. Chain rule again, think of this as cosecant of y. The derivative of cosecant of y is negative cotangent of y. I'm not writing y, I'm writing 3 to the x, that's what y is, times cosecant of 3 to the x, times the derivative of what we designated as y, meaning 3 to the x times ln 3. And these are our two differentiations. And then we have the integral of 1 over x squared minus 1 dx. For this, we're going to do a partial fraction decomposition. 1 over x squared minus 1 is 1 over x minus 1 times 1 over x plus 1. So think of this as a over x minus 1 plus, actually, I don't need the parentheses here, plus b over x plus 1. And multiply both sides by the denominator. That will give you 1 is equal to, when you multiply x squared minus 1 by a times a over x minus 1, you will get a times x plus 1. There will be a cancellation, and then b times x minus 1. If you set x to be equal to -1, then you will get minus 2b is equal to 1, which implies that b is equal to -1/2. And if you get x to be equal to 1, so you plug in the roots of the denominator, in other words, then you will get 2a is equal to 1. You could actually solve this in a more traditional way by forming a 2x2 system, but that's in some sense a very nice shortcut. So that tells you that this is the same as taking the integral of 1/2 times 1 over x minus 1 minus 1/2 times 1 over x plus 1 dx, which is equal to 1/2 ln of absolute value of x minus 1 minus 1/2 ln of absolute value of x plus 1 plus c. Now, how about getting ln of absolute value of x minus 1? This can be justified by the substitution u is equal to x minus 1, and similarly u is equal to x plus 1. Now, let's do the last integral, which is an improper integral. So this is the integral from 0 to infinity of e to the negative x dx. And this has to be interpreted as a limit. So it's the limit as b tends to infinity of the integral from 0 to b e to the negative x dx. The antiderivative for e to the negative x is minus e to the negative x from 0 to b. And this will be the limit as b tends to infinity of negative e to the negative b minus of plus e to the negative 0, which is 1. And of course, the limit of this is 0, which means that the whole thing is 1. So we get finally to this improper integral, which is equal to 1. It converges and it's equal to 1. And that completes our review problems from Calc 1 and Calc 2. And now let's work with double integrals. So the first thing that we would like to do is do the integral of the double integral over 0, 1 cross 1e. So this is the rectangle that has, let's show this, what this is. So on the x-axis, it consists of 0, 1. On the y-axis, we go from 1, I have to go a little bit higher here, something like e, so 1 and t. And pretty much what you do is you form this rectangle. This is exactly the set which is denoted this way. And you want to compute the integral of 3x squared plus 2x ln y. The idea is to write this as a double iterated integral. And the order in which you're going to put dx and dy doesn't really matter here because it's a rectangle. So let's go first with integration with respect to x. So 3x squared plus 2x ln y. Integration will take place from inside to the outside and dy from 1 to e. So what do? You look at the inner function and you think of y as being constant. And what you do is you take the antiderivative with respect to x. So the antiderivative with respect to x will be x cubed plus x squared ln y. And you're going to go from 0 to 1. And then you will have to integrate with respect to y from 1 to e. So if you do your, if you plug in, then you will get 1 plus ln y dy. And the antiderivative of this will be y plus the antiderivative of ln of y is y ln y minus y. and you want to go from 1 to e. So this y cancels with that y, and you get e ln e minus 1 times ln 1. Ln of 1 is 0, ln of e is 1, so this is going to be e. And that's our first problem. Okay, so here, let me just put in a parenthesis. I use the fact that the antiderivative of ln of x is x ln x minus x. This is a simple integration by parts. In fact, it's one of the most fundamental examples of integration by parts. And I would like to go to the next problem, which is the integral. So this is an iterated integral, which means we don't even have to worry about the domain as long as the integration, both integrations are possible, right? So we have x squared plus 2xy is the integrand plus 4y cubed dy dx. So at this point, it makes sense to actually give a brief reminder about iterated integrals. In our context, they're supposed to have come up from a double integral over some general domain. I'm saying general domain since the endpoints are not constant. If all endpoints were constant, then they came from a rectangle. And you don't even need to worry what double integral they came from. In this case, well, the integrand is obviously what you see in front of you, but you don't have an idea about what the domain is unless you try to sketch it. And in this particular problem, there's no reason to do something like that. We will see that there will be such a reason in a situation where the first integration cannot be carried out. But let's wait for that. For the moment being, there's absolutely no problem. We're supposed to integrate with respect to y. That's what it says here. So the antiderivative will be x squared y plus xy squared plus y cubed. And we want to go from x squared to x. And then once we're done with that, we need to integrate with respect to x. So let's plug in. What are we going to get? We're going to get x cubed plus another x cubed plus another x cubed minus, and here we will have x to the fourth minus x to the fifth. That's what we get if we plug in x squared into y in the second term. And finally, we will have minus x to the sixth. And this will give us, I'm sorry, this antiderivative was y to the fourth. Sorry about this. So this will give x to the eighth. Okay. Sorry about this mistake. And this will be which also, of course, should have made this x to the fourth. Okay. So now, what do we get? We will have these two things cancel each other, and we have the integral of 2x cubed minus x to the fifth minus x to the eighth. Let's actually find the antiderivative here. So we will have 1/2 x to the fourth minus 1/6 x to the sixth minus 1/9 x to the ninth. And we want to go from 0 to 1. And this will give us 1/2 minus 1/6 minus 1/9. If we clear denominators here, we will have 9 over 18 minus 3 over 18 minus 2 over 18. So this will be 4 over 18, also known as 2 over 9. And that's our problem. Okay. So in other words, a routine integration, routine to the point that you saw the mistake that I just made. We just have to be careful with what we need to do. But we have a much more interesting situation in the next integral. So the next integral, supposedly, it would have been pretty much like this one. So we want to compute the integral from 0 to 1, and then from square root of y to 1 of 2 to the x cubed dx dy. But here's the problem. I mean, if you try to pretty much do this as a routine integration in the sense that we just did before, it simply doesn't work. Why? Because we cannot find in a simple way an antiderivative for 2 to the x cubed. We have to be careful here. Nobody says that the antiderivative doesn't exist. It exists. It's just that we don't have an easy expression for it. Or I'm sorry, not an easy expression. We don't have an expression for it in terms of functions that we know. Because what we have to realize is we don't have names for all numbers and all functions, and that usually stands between us and writing some functions explicitly. So what do? We entertain the idea that maybe whoever came up with this double iterated integral didn't follow the best option for what variables to integrate with respect to. And we said, could we go back and do it all over again? And the answer is yes, you might be able to do that if you know what the domain was. And that is why it's so important that we actually sketch the domain. So how can we sketch the domain here? Let's look at the fact that we're integrating first with respect to x, and we're actually going from square root of y to 1. What does that mean? That means that we have integration in the horizontal direction, and so we have a left boundary and a right boundary. And the left boundary is x is equal to square root of y, so this is the left one. And the right one, the one on the right, is x equals 1. How are we supposed to understand those things? So x equals square root of y is the same thing as x squared is equal to y, which is your parabola. And x equals 1 is just a vertical line. So the integration takes place somewhere here between these two curves. And the question is, what is the vertical range of this integration? And this you can see it by the limits with respect to y. So it's pretty much from 0 to 1 on the x-axis, from y to the 1 in the y-axis, and then from the parabola on the left to the straight line on the right. So here's your domain of integration, which means that once you have the domain of integration, now you can reverse the order of integration. In other words, you start from the very beginning and you say, now I want to go first with respect to y, then with respect to x. And if you go with respect to y, then you have to talk about a lower boundary and an upper boundary. And the lower boundary here is the x-axis, right? You can see it right here. So this is y equals 0, and the upper boundary will be y equals x squared. So I'm going to go from 0 to x squared, and I'm going to integrate vertically, in other words. And what is the horizontal range of all these integrations? From 0 to 1. One of the things that one should note here is that sometimes there might be a tendency to actually take, try to find the limits of the reversed integral using some general abstract argument. And you have to keep in mind that you have to go through the domain. So here you will have 2 to the x cubed, and you might actually ask what just changed here. And what changed is the fact that now you want to integrate with respect to y, and this is a constant. So the antiderivative is going to be y times 2 to the x cubed from 0 to x squared, and the whole integral from 0 to 1 dx. And that's equal to what? It's equal to x squared 2 to the x cubed integral from 0 to 1 dx. And now everything has changed. Now we have a substitution available. So u is equal to x cubed, du is equal to 3x squared dx, which means that x squared dx is 1/3 du, and you will have 1/3 the integral of 2 to the u du. And now remember, when you do a substitution like this, you have to apply the substitution to the endpoints. And if you do so, you will get the same thing, because 0 cubed is 0 and 1 cubed is 1. And sometimes people might look at this and think that nothing changed for the endpoint, but everything changed. It's just that we are in this happy situation where the changed endpoints happen to be equal to the previous endpoints. So in any case, the antiderivative of 2 to the u, in general, the antiderivative of a to the x is a to the x over ln a. So you will have 1/3 ln 2 times 2 to the u from 0 to 1. And of course, 2 to the 1 is 2, 2 to the 0 is 1. When finally you subtract these things, you will get 1/3 ln 2. And that's it. Finally, we have a fourth problem, which is pretty much of the same type. It's just that the integrand is a little different. And the last problem is to do the same thing for the integral from 0 to square root of pi to y to square root of pi and sine of x squared dx dy. So what do we do here? Again, we're going to go through our domain. So what is our domain? Integration is with respect to x. So we have a left boundary, which is what? X equals y. And we have a right boundary, which is what? X equals to square root of pi. That's a vertical line. So now we have the bisector of the first quadrant, and then we have square root of pi, let's say somewhere here. So this is where square root of pi is. And the vertical range also goes up to square root of pi, which means that these are domain of integration. Okay, so now it's easy to reverse this. And what is the lower boundary? The lower boundary is going to be y equals 0, and the upper boundary is going to be y equals x. So now this integral can be written as sine of x squared dy from 0 to x, and dx from the horizontal range of all these vertical integrations is going to be from 0 to square root of pi. Okay, so again, the antiderivative of sine of x squared, which is constant with respect to y, will be y times sine of x squared. And this will go from 0 to x. And you will have from 0 to square root of pi dx. And this will be the integral from 0 to square root of pi x sine of x squared dx. And now everything has changed. Now you can do a substitution. So u is equal to x squared, du is equal to 2x dx or x dx is equal to 1/2 du. And this will end up being 1/2 integral of sine of u du. And now remember what we said before. We have to go to our substitution and plug in the endpoints into x squared. So 0 squared is 0 again, but now we're going to see the difference. Square root of pi all squared is pi. And here we're going to get negative 1/2 cosine of u. That's the antiderivative from 0 to pi, which is going to give you negative 1/2 of cosine pi minus cosine 0. Cosine pi is negative 1, right? Cosine 0 is 1, so minus another 1. And so this will be negative 2 multiplied by negative 1/2. That will give us eventually the number 1, which is the answer to our problem. And that completes the worksheet for this week. And I would suggest that you go back, redo the problems by pausing the video at strategic points and make sure that you learn this material very, very well. I hope you enjoyed this discussion, and thanks for watching.